Welcome to Spaceverse, your portal to cosmic adventures. For decades, astronomers have been fascinated by the bright, nearby star Vega, a celestial beacon just 25 light-years away in the constellation Lyra. Not only is Vega one of the most luminous stars in our night sky, but it's also one of the best laboratories for studying how planetary systems form and evolve. From the earliest discoveries of excess infrared radiation around Vega in the 1980s to today's high-resolution space telescopes, this single star has challenged astronomers to rethink how solar systems are built. And now, thanks to a powerful collaboration between the Hubble Space Telescope and the James Webb Space Telescope, we have our clearest and most detailed view yet of Vega's enigmatic dust disk, and what we found is surprisingly absent. Despite years of speculation and hope, the latest joint observations reveal a stark and unexpected reality. Vega's dusty halo contains no clear evidence of planets, at least none that are larger than Neptune. Instead, Vega's disk is filled with what scientists describe as a snow of tiny particles, an incredibly smooth, evenly distributed field of dust that lacks the kind of distinct rings or gaps we've come to associate with orbiting planets. This isn't just a scientific twist. It's a cosmic echo of art imitating life. In the 1997 film Contact, based on Carl Sagan's novel, Jodie Foster's character, Ellie Arroway, travels through a wormhole and ends up at Vega, surrounded by dust, with no planets in sight. It turns out that fiction may have come uncomfortably close to reality. It's making us rethink the range and variety among exoplanet systems, said Kate Sue of the University of Arizona, who led the JWST observation campaign. And with good reason. Vega's disk has been on astronomers' radar since 1984, when the infrared astronomical satellite IRAS detected an unexpected excess of infrared radiation coming from the star. That glow, it turned out, came from a disk of dust, the first Kuiper belt-like region ever discovered around another star. That's 8 years before we found even a single Kuiper belt object in our own solar system. What makes Vega so valuable is its orientation. The disk is face-on to Earth, giving us a panoramic view of its structure. And as one of the closest and brightest stars in our neighborhood, Vega has been studied by a variety of powerful instruments over the years, from Spitzer and Scuba to ALMA, and now Hubble and JWST. Each new observation has peeled back a layer of mystery. And yet, the more we see, the more questions arise. The Atacama Large Millimeter/Submillimeter Array ALMA, observing in Chile, refined the initial IRAS data and found that Vega's dust disk starts at about 80 astronomical units O from the star and extends out to roughly 170 O. To put that into perspective, 1 O is the distance from the Earth to the Sun, so Vega's disk spans from 12 billion to 25 billion kilometers, or 7.4 to 16 billion miles. That's a vast stretch of space. The Hubble telescope, using its STIS coronagraph, blocked Vega's glare to observe scattered light in the disk's outer halo, extending all the way to 230 O. But it found that the disk was smooth, so smooth, in fact, that it almost looked artificial. The Vega disk is smooth, ridiculously smooth, said Andres Gasper, another University of Arizona researcher involved in the project. And this is where the mystery deepens. Why is Vega's disk so uniform, while other similar systems, like Fomalhaut, exhibit clear ring structures carved by hidden planets? Both Vega and Fomalhaut are A-type stars, large, luminous, and relatively young, less than 1 billion years old. Both shine many times brighter than the Sun, and both have disks of debris formed from cometary and asteroidal collisions. But Fomalhaut has rings, sharply defined by what scientists believe are gravitational interactions with planets we can't see. Vega? Nothing of the sort. What's the difference? Asked astronomer George Reek, another expert from the University of Arizona. Did the circumstellar environment, or the star itself, create that difference? This question cuts to the heart of planetary science. The JWST's mid-infrared instrument MIRI added a new layer of insight. It zoomed in on the inner part of Vega's disk and confirmed the Kuiper belt-like region detected by ALMA, capturing thermal emissions from slightly larger particles, roughly the size of sand grains, unlike the smoke-sized particles visible to Hubble. This kind of particle size sorting is crucial. It tells astronomers about the forces acting on the dust and, in turn, about the dynamics of the entire system. There must be a large swarm of asteroids and cometary bodies shedding dust, said Skylar Wolf, who led the Hubble observations. According to her team, Vega's light plays a major role in sculpting the disk. The intense radiation from the star pushes the smallest particles outwards, sometimes onto hyperbolic trajectories, meaning they'll escape the system entirely. So while there may be no planets as large as Neptune or Jupiter, Vega is far from quiet. The JWST also detected something that might hint at more activity, a drop in brightness at around 60 from the star. This isn't a gap in the traditional sense, like the one seen in Saturn's rings, but rather a dip in dust concentration. Interestingly, this dip varies with infrared wavelength, suggesting it's linked to the size of dust grains in that region. Two possible explanations have emerged. First, there's the Poynting-Robertson effect, a process where radiation from the star causes dust particles to spiral inward slowly. The particles lose momentum and fall closer to the star, creating a drop-off in their population around certain distances, particularly if the particles are around a millimeter in size. The second explanation? An unseen planet, potentially around 6 times the mass of Earth, may be shaping the disk from within. It's not massive enough to form obvious rings, but just enough to influence the dust density in the region. Still, there are no direct detections of such a planet. And with current technology, anything smaller than Neptune is hard to confirm with disk imaging alone. The architecture of the Vega system is markedly different from our own solar system, said Wolf. In our system, gas giants like Jupiter and Saturn act as shepherds, keeping the dust in check. Without such gravitational gatekeepers, Vega's dust spreads far and wide, creating the diffuse halo we now observe. There's another challenge, though. Neither Hubble nor JWST can peer all the way into Vega itself. The JWST's inner detection limit is about 7.0, roughly the distance from the Sun to Jupiter. But modeling suggests that the inner edge of Vega's disk lies between 3 and 5.0. This raises the possibility that a planet inside this hidden region may be carving that sharp edge, much like how Saturn's moon Pan carves a gap in its rings. In fact, computer simulations show that even a single Earth-sized planet could account for the structure we see, though it would remain undetectable for now. There's still a lot of unknowns in the planet formation process, said Sue. These new observations of Vega are going to help constrain models. In astronomy, constrain means narrowing down the range of possibilities. When you observe something like Vega's disk, you can use the structure and behavior of the dust to rule out certain planetary scenarios. Over time, this helps refine our understanding of how systems evolve. It's also worth noting that Vega spins rapidly, much faster than our Sun. Its rotational period is about 12.5 hours, which flattens the star into an oblate shape and affects its gravity field. This could have major implications for the disk and the dynamics within it. Additionally, Vega has a debris replenishment problem. The dust we see today can't be billions of years old, it would have been blown away long ago. That means the system must be actively producing dust through collisions between asteroid-like bodies and icy comets. In essence, Vega's disk is alive, constantly refreshed by cataclysmic impacts. These new observations bring us closer to understanding the immense diversity of planetary systems. Vega might not have giant planets like Jupiter, but it teaches us something equally valuable, that not all solar systems follow the same blueprint. Some are neat and sculpted. Others, like Vega's, are smooth and stormy, defined by subtle effects and processes we're only just beginning to grasp. The findings from Hubble and JWST will be published in upcoming issues of the Astrophysical Journal, expanding the frontiers of what we know about circumstellar disks, dust dynamics, and the hidden architectures of planetary systems. Whether Vega hides small worlds in its inner regions or is simply a planetless star wrapped in ancient dust remains to be seen. But one thing is clear, Vega continues to surprise us. And in that surprise lies the very essence of astronomy, a never-ending journey to understand our place in the universe. If you enjoyed this deep dive into Vega's mysterious dust disk and the latest insights from the James Webb and Hubble Space Telescopes, don't forget to like, subscribe, and hit the notification bell to stay updated on the wonders of the cosmos. From dust and starlight to distant worlds and new beginnings, there's always more to explore. This is Spaceverse.